Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello? Oh. Great. So I'm really happy to have Suman here today to give us a talk about his work from CMU. And he also collaborates with people from, closely with people from Intel Pittsburgh Research Lab. So I think his interest lies in sensor networks, distributed systems, and databases. So it's really good to have him tell us what he did and how he built the IrisNet project, which is basically a very big project for Intel Pittsburgh Lab. So I'll give the stage to Suman. Welcome, Suman.
Thanks, Alec. Good morning, everyone. I am Shumon Nath from Carnegie Mellon University. Today I'll be talking about how we can build robust sensing application by exploiting redundancy. So over the last few years, we have seen a number of real-world applications that use data from live sensors. And the sensors can be very different in nature. For example, they can be microsensors or motes, which are small wireless devices, battery powered, and they have a number of sensing components, for example, thermometers for sensing temperature. The sensors can also be more powerful, like microphones or webcams that are directly connected to the internet. Okay? And those sensors have allowed the scientists to monitor the physical world more closely. For example, the ecosystem monitor at James Reserve, California uses microsensors to monitor how environmental factors like temperature or humidity affect the ecosystem. The ocean monitor system at Oregon coast uses cameras to monitor interesting events on the ocean surface to detect oceanographic events. The same sensing application can use different types of sensors. For example, the ocean monitor can also use motes to sense temperature of the water so that scientists can correlate the temperature with the other events. Okay? So those sensors are becoming more and more ubiquitous nowadays. But we actually haven't seen a lot of applications on top of that. And I believe that it's mainly because writing an application on top of sensors is very difficult. For example, writing an ocean monitor requires mechanisms for data collection and filtering, for indexing and storing that data, for processing users' queries on that data, and a lot of other distributed systems issues like fault tolerance, load balancing, security, privacy, and so on. And this is a very complex task. The general goal of my research is to simplify those tasks for general people who want to run their own sensing application. And towards that goal, in collaboration with Intel Research Pittsburgh, I have designed and implemented a software infrastructure called IrisNet. IrisNet stands for Internet Scale Resource Intensive Sensor Network Services. And this is a software infrastructure that people can use as a tool to build their own application. IrisNet has a two-tiered architecture. On the edge, it has sensing agents that run on laptops or PDAs or base station of wireless sensor networks. And those sensing agents collect and filter the sensor data. And IrisNet provides APIs for collecting that data scalably and some issues like security and privacy. On the core, we have organizing agents that run on internet connected hosts. And those organizing agents basically collect the data and they organize that data so that people can make high-level queries on that collected data. Note that this infrastructure is a shared infrastructure, which means that more than one applications can run on this infrastructure at the same time. And IrisNet provides an application programming layer so that someone can customize this infrastructure to write his own application. Okay. So currently, IrisNet consists of around 30,000 lines of C and Java code. It's an open source project. And we have a number of real applications that use this infrastructure. The first application is a network monitor application that I developed and deployed on around 450 nodes on Planet Lab. And in this application, we use software sensors, which are basically programs that gives useful statistics about the machines, like the bandwidth usage, memory usage, processing load of the machine, and so on. And user can make high-level queries to see how the resources are being used in this infrastructure, or to discover resources like the machines which have reasonably low processing power so that people can run their experiments on those machines. The second application is a ocean monitor service that I described before, and it was developed by a group of oceanographers at Oregon State University. They used our code to write their own application, and this is the snapshot that we got from that particular prototype that they had built. Okay. So in IrisNet, we have addressed all those basic functionalities that I show here, and of those, I have worked on the components that shown in this blue color box. But in this talk, I will talk about only one particular component of this whole architecture, which is fault tolerance. I will show how we make the applications built on IrisNet more robust, and that will be the focus of the talk. But if you are interested, I can talk about the other components after the talk. Okay. So why robustness is important? First of all, those applications are generally deployed in harsh environments where failures are very common. And they are deployed in remote places, and they are mostly unattended. For example, in the ocean monitor system, if something breaks down, a scientist or someone needs to go to the coast to fix this, and this is very inconvenient. And more importantly, some of those applications become more useful when there is some disaster. For example, in the ocean monitor system, an ocean storm may bring down a significant part of the infrastructure. But the same ocean storm may generate interesting events that scientists want to know. So it is desirable that the whole system continue running even when a big part of the infrastructures are down. Similarly, a sensing system deployed in a building may become more useful when there is a fire in that building, because the firefighters may use that same system to locate and rescue the people within that building. Okay. So at a high level, the sensing system composed of two components: the data collection components that collects the data, and the second component is the data storage component, where people make high-level queries on that collected data. For end-to-end robustness of this whole system, we need to make both those data storage and data collection component robust. Simply making only one component robust is not useful. We need to make both of them robust. Okay. So in this talk, I will talk about robustness of all those different components. But the robustness component of collecting data from internet connected sensors is not very challenging, mainly because they don't have any energy constraints and they are connected through good internet connected links. So in this talk, I will not focus on that. I will focus on how we can make the data collection component from wireless sensors robust, and how we can store that data on the internet connected host robustly. Okay, so that will be the focus of this talk. So unfortunately, it is very challenging to make those two components robust. For example, think about the wireless sensors. They are generally deployed on harsh environment where the loss rate can be really, really high. For example, people have found that average loss rate can be as high as 30%. Then those sensors have limited battery power, and therefore to reduce or to save expensive communication, those sensors generally use unreliable communication. So they don't have any acknowledgement or any retransmission mechanism, because that requires more resources. Now, in such constraints, when the base station wants to collect data from the whole sensors, because of this high loss rate and because of this unreliable communication, the base station ends up collecting only, say, 40% of the data. 60% of the data gets lost within the network because of high loss rate and unreliable communication. One way to address that is to use reliable communication protocol by using retransmission or some error correcting code and so on. And by doing that, we can increase the amount of aggregated data or the collected data. For example, we can collect around 98% of the data. But the problem is it has huge overhead. For example, it reduces the channel capacity by 25%. It increases the latency by 3 times. And more importantly, it increases the energy consumption by 3 times. And since those sensors have limited battery power, which means that the effective lifetime of those sensor networks are reduced by around 3 times. So in my research, I have shown that we can still use unreliable communication, so that we are still using minimal amount of resources, but we will use a special class of algorithm that will give us 98% of the data. So in other words, my research has shown that we can actually achieve the best of both those worlds. And the trick that I use in this class of algorithm is to use a special class of algorithm that exploit the broadcast medium which is already available there. This is only the communication failures. If you consider the node failures, that will be worse. Well, so this 40% is actually also depends on like what's the topology that you are using. Right, yeah, multiple hop, sure. Yeah, it's multi-hop network, yeah, that's true. Okay. So later in my talk, I will show how we can actually exploit the broadcast medium to achieve that. Okay. Similarly, storing data on the internet reliably is challenging, mainly because of the different types of failures that we see in the internet. And the traditional approach of making this robust is to use techniques like replication or quorum systems, etc. My experience of using those traditional techniques on sensing systems showed that those techniques do not work very well in wide area systems. And in particular, in one of our applications, even after we replicated the data 7 times, we saw that 1 out of every 100 requests failed, which is not acceptable for many applications. So in my research, I have shown that we can exploit something about those functions of those applications that will improve the robustness by an order of magnitude by using less resources. And later in my talk, I will show how we exactly do that. And the trick here is to exploit the fact that sensing services can occasionally tolerate stale data. And later in my talk, I will show what I exactly mean by that. So in summary, my approach of building robust application is to use domain-specific properties. For example, the broadcast medium or tolerance for stale data, and to use them efficiently for using redundancy. By redundancy, I mean excess resource that can be free. For example, the broadcast medium is already there, or it can be something that we intentionally employ, for example, replication. And in this talk, I will present techniques for 2 times more reliable data collection in wireless sensor network that doesn't have any additional energy overhead. I will technique solutions that makes the storage component an order of magnitude more robust, again, without any additional resources. And then I will talk about the design and implementation of those techniques in a real system. Okay. So is there any question till this? Okay, so now I will talk about the first component of this end-to-end robustness equation, which is how we can make the data collection part robust. Okay. One of the important tasks in sensor network, wireless sensor network, is to collect aggregate data. For example, average temperature sensed by the sensor, or to count the number of live nodes in the network, and so on. And the traditional approach of doing that uses 2 techniques. First, it constructs a spanning tree that spans all the nodes in the network and where the base station is the root. And then every intermediate node in the tree aggregates the data as the data propagates toward the base station. This is called in-network aggregation, and it is used in all the current existing systems like TinyDB or Cougar. The advantage of this technique is that every node needs to send exactly 1 small message, which is the aggregation of the result that it got from all of its children. So it is very, very energy efficient. But the problem here is that it is not robust against node and link failure. This is very fundamental to tree topology. Right? For example, if a single message is lost, for example, that particular message, then the whole subtree below that link will be absent from the answer computed at the base station. So instead of 10, we will get a value 3 here. Right? And this is a big problem, and that's why we get only 40% of the data. Okay? And as I mentioned before, one way to fix this is to use reliable communication. So the node can retransmit the data again if it is lost. But as I said before, it has 3 times more energy overhead. So I will not consider this type of approach here because I will show that we can actually do better even without this type of retransmission. So this is just a snapshot, right? So data loss rate is defined over a time. Oh, so here I am saying 30% because instead of 10, you are getting 3. So you are actually getting data from 3 sensors, right? Because I mean those 3 sensors are able to talk to the base station. So in this particular snapshot, it's only 30%. Yeah. Okay, so now note that here the sensors are actually using a broadcast medium, which means that when a node sends its message, it can be actually received by multiple of its neighbors. And now if we let all those neighbors to use that data for in-network aggregation, then we get multipath routing. And it is definitely more robust than well, it definitely depends on the topology that you are talking about. If you have a chain topology, then definitely you probably can't make multipath routing out of that. Oh, so even in the coastline, it's not a chain topology. So they basically, every sensor can actually talk to multiple neighbors. So there is some redundancy there in the deployment. So people generally deploy in a dense deployment so that there is some redundancy so that even if one sensor fails, the other sensor can do something there. Okay? So the assumption there is that, yeah, you have multiple neighbors, you're not just one neighbor. Okay? And this multipath is more robust than tree because even if one node or link fails, there is a possibility that the data can reach to the base station through an alternate path. And since every node needs to broadcast exactly once to talk to all of its neighbors, it can be very efficient. And actually in this particular example, in terms of number of transmission, it is actually same as the tree because everyone is sending its data exactly once. Okay? So then the question is, why does the traditional approach don't use these type of techniques like multipath routing? Why do they use tree? The reason is double counting. So what happens is if we use multipath routing and if the same data is sent to multiple of its neighbors, if all those neighbors count that data in the aggregation, at the base station you get an overestimation of the actual data because you are counting the same data multiple times. So for example here, instead of 10, we get 58. And this is not the only problem. For some aggregates, ordering is also important. And since here there are multiple different paths a data can reach the base station, the ordering can be different. Okay? So those are the problems. That's why people don't use multipath in traditional aggregation scheme. So the main challenge here is the following. If we really want to exploit the broadcast medium and use this type of multipath, then we need to somehow make this aggregation process order and duplicate insensitive. Which means that no matter what topology you are using, no matter how many times you double count a value, at the end, at the base station, you will always get the same answer. So we sort of get rid of this double counting and different ordering problem. So that's the, okay. So this is just an example aggregation, but it can be very different types of aggregation. Right? Okay. Sure. Okay, sure. So yeah, you are right that if you actually want to collect all the data, then this technique won't work. So here I am talking about only aggregation of data so that you are doing some sort of compression on the data. So for example, when you are collecting all the data, even there, you can probably compute some sort of sampling. That sampling is an aggregation too. And we can actually do sampling over this type of framework too. And Okay, actually later I will show that actually this scheme can be generalized for data collection too. And the way you can do that is you can use some sort of erasure coding, like erasure encoding, so that it's m out of n type of encoding. So the way it works is that you have some data, you break it down into say 10 pieces, then you encode the whole data into like 20 pieces. Then you can reconstruct the data if you can get any 10 of those 20 pieces. Doesn't matter which 10 you have got. So if you can encode the data in that way, then you can use this type of topology to collect all the data. And that will give you significantly more robustness. But in this talk, I will not talk about this data collection problem. I will talk about only the aggregation problem. Okay. Yeah. And okay, so if I allow you to retransmit, then probably you'll retransmit more than twice on average because the loss rate is high. So even if you are doubling the transmission cost, even after that you will win because of that encoding scheme. That's right. Okay, so then the question that I'm trying to ask here is it possible to compute the basic aggregates in order and duplicate insensitive way? Okay. And I have shown that it is actually possible. And to give you an idea, here I am showing a very naive algorithm. Okay. So this is not an efficient algorithm. I will show it just to show the idea that what we do. So suppose the goal here is to count the number of live sensors in the network. And the topology that we are using is this. It's one type of multipath routing. So the way the algorithm works is the following. Every node in the sensor has an ID, and it generates a bit vector where the bit given by the ID is set to be 1 and all other bits are 0. Okay, and all the sensors do that. Then every sensor broadcasts its bit vector, and when a node gets a new bit vector, it combines those two bit vector by using the Boolean OR function. So that now this bit vector contains two different ones because it did Boolean OR. And this process goes on as the data propagates towards the base station. And finally at the base station you get a bit vector that contains all the 1 bits. And finally you simply count the number of 1 bits and return the result to be 4. So intuitively this algorithm works because we use Boolean OR function that preserve those 1 bits. And it is also order and duplicate insensitive because the Boolean OR function itself is order and duplicate insensitive. Doesn't matter how many times you apply the Boolean OR function, the result will be the same. Okay?
Seems like you have to assume the data itself.
Okay, sure.
Otherwise, it reverse order with the receiving order is not the same. The sending order, you might have overlap.
No, so in the first step, I actually generated those bit vectors, right? So that bit. Okay. So in general, whenever you generate this bit vector or something like that, you basically generate it once and then compute the aggregate over that representation. That doesn't change over time. So even if the data changed, say for example, instead of counting the number of sensors, we are counting some number of events. Okay. So now suppose I generated those bit vector, and when the aggregation is going on, suppose in one of the sensors the total number of events changed. It became 2 from 1. But in that case, I am actually not changing the bit vector. I am using the old bit vector that I am using. So I am basically getting a snapshot of whatever we had at that particular time.
Can you take the snapshot network-wise?
No, I mean if it is not synchronized, that you can do that. So it's some sort of loose synchronized.
The order you set is between that.
Right, exactly. Okay. So now there are a couple of things about this particular algorithm. First of all, at a high level, we wanted to compute count. But within the network, we used all different types of functions, and those functions may not have anything to do with the actual count function. For example, we used a function that generated the bit vector. We used Boolean OR function or count 1 bit function. And those 3 functions are chosen in a way that they have certain properties that give you the order and duplicate insensitivity. And they 3 in combination give you the same effect that you want from the target function. For example, here they all in combination give you the count function. Okay? So when you try to compute some aggregate, you need to carefully choose these type of functions. Okay. And second, within the network, every node exchanges some data structure, which we call synopsis. For this particular example, synopsis is the bit vector. But for other aggregates, it can be different. It can be like a sample of data, a histogram, or it can even be a simple number. Right? It depends on what aggregates you are actually computing. And finally, the synopsis needs to be small just to make the whole algorithm energy efficient. And in that respect, this particular algorithm is not efficient, because if you really want to have this type of bit vector, the size of the bit vector needs to be at least the number of nodes in the network. Like it's order n. So that's why this algorithm is not efficient. So one way we can make this algorithm efficient is to use a smaller bit vector. And then we let each of the sensors to probabilistically set one bit within that bit vector. So now what will happen is, since we don't have as many bits as the number of nodes, sometimes some node will set, sometimes two nodes will set the same bit. So in the base station, we won't get the exact answer. We get only approximate answer. And we have an algorithm that uses only logarithmic number of bits, and it gives an approximate answer. But the nice thing is that it has very nice approximation bounds, and the result is within like 10% of the actual count. And we call that efficient because it's logarithmic size of bit vector.
How do you pick the size of the
So since it's logarithmic, it actually doesn't matter. You can just overestimate, right? Or you can basically look at the ID of the sensor and see like what is the size of the ID. You can just use those many bits.
So you take it to an argument which is better than a big vector. Create an order n right off.
Sure, sure.
So it seems a little bit, by the way, if you're really to scan everything or really kind of get, then the ranking is very good. The order is the more expensive, so you get If I get an object transfer one bit,
Yeah. So definitely the Naive algorithm is not the one that you are using. It's definitely cheating, right? But since this algorithm is logarithmic size bit vector, which means that even if you use tree, if you are counting the number of nodes over a tree, you need logarithmic number of bit vector or count. The count will be logarithmic in terms of the number of bits. So in terms of the number of bits, even if you are using this algorithm versus what you use in a tree algorithm, that's same. So you are not using any extra resources here. But you are right that here we are using extra resource. But as I said before, this algorithm is used just to give the idea of what we do. Okay? No. So that's what I'm saying, that this new algorithm needs only logarithmic number of bits. So if you have number of nodes, if you have like 1024 nodes, you will need only 10 bits. So that's how the efficiency comes from. Okay. I have a backup slide. I can talk about that later.
So if you like, so in that case, like you get using a 10-bit vector, comes up to the top, you've got 8-bit set, and you like guess it's 256.
Yeah, it's actually exactly like that. So basically, what we do is we look at the final bit vector, and we see what's the highest bit that is set in that bit vector. Then we take 2 to the something, 2 to the that bit vector, and then we need to use some sort of scaling factor to avoid some error. So, but the idea is the same. Yeah, so I can actually show you the algorithm later. Okay.
Yeah, I see the max obviously.
Exactly.
And work.
Yeah, so that's true. Okay, so the general framework that we proposed is called Synopsis Diffusion, and we have shown that this framework is general enough to support a number of different queries. For example, here is the list of queries that we can compute within this framework, and it has sum or average, distinct count, uniform sample, and you can actually compute a lot of things from the sample. and number of iceberg queries, top K queries, etc. So, okay. So iceberg queries is you give a threshold and you compute all the data above that threshold. Sorry. Okay. So some of those algorithms are slightly complicated than the naive algorithm that I presented. And one of the problem we had in designing those algorithms was like how we actually prove that it is order and duplicate insensitive. And if you try to prove that in terms of the multipath routing, when as I said, our main requirement is that no matter what topology you are using, at the end you should get the same result. Now, one naive thing you can do is basically you can generate all possible topologies and see whether the algorithm is actually giving the same answer. But that's not feasible. So to address that problem, we formally started this general class of algorithms. And one of the major contribution of this work was that we provided the necessary and sufficient conditions for an algorithm to be order and duplicate insensitive. So what it means is that suppose you design a new algorithm and you want to prove that the algorithm will really work. You simply use our result, and the properties that we require are really simple. And if you can show that your algorithm shows those properties, then the algorithm is correct. So it will basically help you in designing new algorithms. And many of those algorithms are approximate, mainly because we are using those smaller bit vector type of things. And then another question that comes is that how you actually analyze the approximate error of these distributed algorithms. And we have also showed a framework for analyzing those algorithms. So I'll not talk about them here, but I can talk about them later if you want. Okay.
But in any video application, it's almost like broadcasting the topic. So you cannot send only like once. It cannot be like a wave coming towards the destination.
It can be. It depends, like if you want to compute just once, then it will be just one wave coming to the destination. I see. Okay. So basically the way it works is that so nodes are sort of very loosely synchronized. So every node knows what its destination is, and a destination node sends only after receive, right?
So basically I have to go
Exactly. So this is some sort of common assumption in all the database type of aggregation. So that synchronization is already there. Okay.
So how do I know I'm on the edge?
Yeah, so I will actually talk about them later in my talk. I'll show how we actually construct this topology.
So when you construct the routing, it seems like it still needs some order, right? You don't want to break loose.
Yeah, sure.
How
Okay, so I will actually go into the topology part later. I will go into that. Okay, so here is some results that we had using a synopsis diffusion algorithm and the traditional tree-based count algorithm. So the count algorithm used on tree, that's the exact algorithm. It doesn't have any approximation error, but the synopsis diffusion algorithm has the approximation error that I mentioned before. So the x-axis here shows the loss rate, and the y-axis shows the root mean square error. So when the loss rate is very small, say 0, tree is better because it doesn't have any approximation error. But synopsis diffusion has the approximation error when there is no loss. But when the loss rate increases, the RMS error of tree goes sort of exponentially. Whereas that for synopsis diffusion is very stable over time. And if you look at the typical loss rates in this type of network, you will see that the RMS error for tree is significantly higher than that of synopsis diffusion. And for synopsis diffusion, actually here, the most of those error is actually coming from the approximation error. And you have nice bounds on that approximation error, so you have better semantics.
Is this a loss rate of 1 hop?
This is average loss rate over all the nodes. For 1 hop, exactly. Yeah. That actually does matter. So definitely the results here actually depends on the topology that we constructed. So what we did here is that we took topology that was in one of the real deployment at Berkeley lab. So in this particular example, I think the maximum number of hops are 5. So the depth of the tree was 5. I mean, if you increase the depth of the tree, it will be worse. Okay. So this is in terms of the RMS error. So then the question is whether we are spending more energy for that. And the numbers here show that synopsis diffusion is actually almost as energy optimal as a tree. So those two numbers are very, very close. So what it shows is synopsis diffusion, it can be as energy optimal as tree, but it is significantly more robust than a tree. Okay. So we are actually getting, no, there is no retransmission. Yeah, sure. In this particular example. So what we are getting here is that significantly higher robustness without any energy consumption. Okay. Okay, so now I will come to the topology component. So far I have talked about the technique that we can use for aggregation, and that technique must run over some topology. Okay. And in traditional scheme, the topology is always a tree. You can't use anything else tree. But since synopsis diffusion algorithm is order and duplicate insensitive, you can actually use any topology underlying the aggregation. So this actually gives you the freedom of optimizing those two components, aggregation and routing independently. You can use whatever topology you want. Okay. So now I will talk about a number of topologies that we used in our work. And the basic topology we used is called rings. And the basic idea is to organize the nodes in a number of rings so that a node is in ring I if it is I hop away from the base station. So you asked like how the ordering is established. So the ordering actually established in this way. So the base station broadcast, and as the message goes towards the outward edge, every node basically remembers who is the guy he first heard from. And that's his neighbor that he needs to send the data to. Okay? Yeah, I will actually address that issue later. So right now, just assume that it's symmetric. Okay? So I will actually talk about how we deal with asymmetric links. So if it is symmetric, then if this guy hears from this guy will assume that it should send the data to this guy. Okay? And then when a node broadcasts its message, this is received by all the neighbors in the next ring. Say for example, nodes here broadcast, it's received by all the neighbors here. Then in this way, data just propagates towards the base station. Right? So basically, every node sort of needs to know what its ring number is. Ring 1, ring 2, ring 3. And that will decide, that will basically tell you when you should turn on your radio. You actually don't know how many neighbors you have or who are your neighbors. You simply know that this is the time window that I should expect some packet from my neighbors. So that's the synchronization that I am talking about. Okay? So this is which assumption? The broadcast? Yeah. Yeah, but in tree, although you have a lot of neighbors, you have only one guy who will actually use that data. All other guys will simply discard it. So here I am saying that all the neighbors that are in the next ring and hear you, they will actually use that data for aggregation. Mean they actually use that, yeah. Yeah, right. Yeah. So definitely. How I construct the ring? Oh, so we use this because first of all we need to some sort of do synchronization so that every node knows when to turn on its radio to receive that message. And the ring number actually tells you when to turn it on. Yeah, this is for energy savings, right? And the second reason is that by using this type of structure, you don't have any loop. It always propagates towards the base station. So you get a directed acyclic graph instead of a general graph. No. It's not that. Okay. So it basically. So one of the assumptions here is that the base station will eventually hear from everyone, and the result that you get at the end, it's actually valid over the data that you have heard from. So now if there is a loop and the data never reach the base station, then the result that you get here, it's not valid for those data because they are just missing. Okay. Well, so if you synchronize it very carefully, then this will probably turn off its radio by that time. Oh, it doesn't need to hear this because this guy will hear the data from this guy. It will just ignore it. Yeah, right. Yeah. I mean, it doesn't matter. I mean, if you actually allow ring, that's fine. What will happen is you need to wait for a longer period of time here to get all the data. Now you exactly know that after 4 epochs, you will get the data because that's the depth. Hmm. Right. Right. So the aggregation scheme has the resilience of double counting, and this particular topology is not a requirement for this synopsis diffusion algorithm. This is something that has some nice property. Nice properties is, first of all, it is as energy efficient as a tree because every node transmits exactly once. It has no loops. So basically the base station knows when it should expect all the data. Basically that's the maximum number of loops. But you are right that for doing that we are actually giving up something. For example, it might happen that both those links fail and it actually can talk to the base station in this way. But if we allowed this guy to talk to this guy, then the data could probably move in this way and reach the base station. So we are actually no, that doesn't. That doesn't. It doesn't affect. No, no. Because it's order and duplicate insensitive. No, 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 no. No, no, no. The algorithm is independent of topology. It has nothing to do with topology. You can use whatever topology you want. The correctness is still there. Yeah, right, exactly. So this is one particular topology that we use for energy savings. Yeah, right, right. Is it?
I think that the routing would be disastrous, but it actually doesn't violate the correctness.
Exactly.
Of things that's received in the base station.
Right.
Yeah.
Yeah. Yeah, sure, sure. So you can actually do a lot of optimizations here, and that actually comes from the fact that our aggregation scheme doesn't depend on the routing layer. You can do whatever you want. Any clever tricks you can. So this is a very basic topology that we are using. And later actually I will show how we can enhance this basic topology in a number of different ways.
Imagine that you didn't want the one-time count, but you constantly want
Okay, sure.
assuming the network is very long way.
Mm. Mm.
So what you want to do is constantly count.
Right.
But it works to have a trivial algorithm like this that says every 20 seconds, transmit the packet, which is my current packet.
Okay.
And then for the next 20 seconds, looking and then potentially again.
Mm-hmm.
So with all the what is the method?
So you are basically talking about like continuous queries. The queries basically run over the network. So if that's the case, then you basically need to start a new phase of the aggregation after the first one finishes, right? Because you don't. Yeah. Sure. Yeah, sure. It will converge. So the thing is the following. So if you start a new phase of aggregation before the previous one finished, then the semantics of the answer may not be clear because you got data at different timestamps. But if the data doesn't change that much often, then you are right. You will get the correct answer. It doesn't hurt. Yeah. So. Right. 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 Yeah. I mean, you'll use more energy. Okay. Okay, so the nice thing about this one is that it is as energy efficient as a tree, but it is more robust because it is multipath. Okay, so now I will talk about two enhancements of this basic topology. So the first enhancement comes from a feature of synopsis diffusion algorithm. Okay? So every synopsis diffusion algorithm, because of the formal framework that we have, has the following property. For example, suppose in this example we are using the naive counting algorithm that I described before. So node A is taking all the bit vectors, taking Boolean OR and sending it. Okay? Now the property is the following. The property is that if you take the output of this aggregation and if you take any one of the inputs, say for example this one, and use the same aggregation function, then the output doesn't change. It will always be the same. And it's true for any synopsis diffusion algorithm. Okay? Now suppose the message from B to A gets lost. In that case, A will form a synopsis which is a Boolean OR of other two bit vector, not this one. Right? And suppose B overhears what A has forwarded to its next hop. And now if it checks the invariant, it will see that the invariant doesn't hold. And then it can immediately know that the data that it sent to A hasn't reached A. So in some sense, it is getting a negative acknowledgement of the data delivery. And it is implicit because node A doesn't need to send a message to this guy because that can be energy expensive. And note that this is not true for the traditional approach. For example, suppose this is the tree-based approach. We are doing sum. So node A basically adds up all the values from the children. Now if this link fails and if A forwards a value 9, B doesn't have any way to say whether that 9 includes 6 or not. It may or it may not. So it doesn't work for the traditional approach.
Independent collision is pretty small, right? And if the collision is in the book of the data, that makes it null.
Well, so I am assuming that if you receive a data, you receive it correctly.
No, I mean, if the other stream, right, if the bit is colliding, then you just implicit acknowledgement.
Yeah, right. So it,
and
right.
If that bit is the most significant bit, that is
Yeah, so you are right. So if, so suppose it might happen that this bit was set even here, right? So then this bit will be set here so that this guy actually will not know what's going on. But the important thing is that in that case, this particular synopsis, it is not necessary for the aggregation. It is useless anyway. So it doesn't hurt your correctness. Yeah, it's redundant anyway. So that's the nice feature that each of the synopsis diffusion algorithm has. Yeah, so I mean, even if you assume that you are listening, you cannot do the same thing because this 9, it may contain 6 or may not. So assumption is that you are hearing your parent but not your neighbors. Right, exactly. So if you hear only your parent, you can't do that. Oh, so in traditional techniques, you don't use the, you can use definitely because we are saying that synopsis diffusion is independent of topology. Sure, you can use a tree, doesn't matter. Yeah, right. Yeah. So we can use this technique to estimate the link quality within the network and to adapt the topology if things change. Okay. So for example, suppose this is the rings topology and different color here shows nodes at different rings. So now, suppose every node, for example, this one uses this implicit acknowledgement mechanism to estimate the quality of the links. And if the quality link is bad, then it can simply switch itself to a new ring so that now it has a different set of neighbors to talk to the base station. So it can basically adapt these things continuously when loss rate or other things in the network changes. So by switching, I mean the set of neighbors that you talk to. You basically change that. So previously, it was talking to this sort of neighbors because it was in ring 2. But now it will be in ring 3 so that it can talk to ring 2 neighbors. So it basically changed the set of neighbors you talk to. And this may be very useful when loss rate changes or there are some obstacles in the network. You can adapt the network accordingly. Yeah, you can do that. Sure. Sure.
You can put it through.
So it depends on how often you do that. If you do it like very infrequently. So if these nodes, they do not change the rings at the same time you do, then you won't create a loop. No, right, exactly. Right, exactly. Yeah. Right. Yeah. Right.
Ultimately, what we really care about is on an aggregate, not accurate. The structure that the next one is not very easy to go back to everyone. Essentially, the tree structure is very restricted in the sense that it's something like
Yeah.
this structure is not as restricted.
Yeah, exactly. Right. Right.
So it seems like the ideal thing would be to have someone who decide whether the aggregate is accurate or not. If it's not accurate, then we use the structure.
Yeah, so I will actually talk about that in the next optimization that we do. So yeah, so in this optimization, basically every node independently take a decision, and if you are not doing it very frequently, then the expectation is that probably not all the nodes are doing the switching at the same time. So you put some sort of randomization there. So we have seen that if you put some sort of randomization, some simple randomization there, it converges to a pretty good thing.
Yeah, like someone is very like, but we can even then the packet coming or the way.
Yeah, so it's not just like this, right? I mean, if you see the condition actually improves, that you can move back to the previous ring. So things can stabilize in that way. Okay. So we call this particular optimization adaptive rings. The second optimization comes from the trade-off between synopsis diffusion and trees. So for synopsis diffusion algorithm, the communication error is very small because you are using multipath routing. But the approximation error is high because most of the algorithms are approximate anyway. Okay? So when the loss rate is very small, for example, if you deploy the sensors in some controlled environment, you probably would like to use tree instead of synopsis diffusion. Another trade-off comes from the message size. For some of the aggregates we have, synopsis diffusion uses bigger message than tree. So depending on the amount of energy you have, the application may or may not decide to run synopsis diffusion. It can choose tree. So those trade-offs have led us to the following two questions. Can we combine the benefit of those two approaches? And second, can we dynamically adapt the topology as those constants change over time? Okay, so for example, if loss rate change, if loss rate is small, we should use tree. If the loss rate is high, we should use synopsis diffusion. Can we do it automatically? So we have addressed those two questions in a recent work, which will appear in Sigmod. And here, I don't have time to talk about all the details here, but I will talk about a example topology that we use there. We call our topology tributaries and deltas. So the basic idea is to use multipath routing near the base station, and we call that region the delta. And to use tree topology on the edge of the network, which we call the tributary. So the intuition here is that the messages near the base station, they are more important because they carry more aggregate data. So we should save those messages, and to provide robustness to them, we use multipath near that base station. But the messages here, they are actually not carrying a lot of aggregate information, so they are less important. Okay? And it seems that using this type of hybrid topology is not straightforward. You need to maintain some sort of correctness condition on every node. And we have formalized that, and we have shown that every node needs to maintain a very simple invariant to ensure the correctness of this topology. And our construction here is adaptive. So based on the loss rate, the delta region, it can shrink or it can expand. And that decision will come from the base station. As Venkat mentioned, that if the base station decides that there are lots of error, it can decide to expand this delta region. So what we do is, suppose you are computing some aggregates, say for example, average or sum. Along with that, we also compute the count aggregate. So from the count, you know how many guys you have heard from, right? So the way it works is that, so if the loss rate is pretty good in the network, then basically the delta region shrinks. and almost all the nodes use tree, because tree gives you the better guarantee in this scenario. And if the loss rate increases in some part of the network, then the delta region can basically expand in that region, so that you now use multipath on that part. Okay? So here is the experimental result that we have. In this experiment, we put the sensors in a square region, and we fix the loss rate to be 5% in 3/4 of this deployment. And in 1 quadrant, we vary the loss rate. That loss rate is in the x-axis. The y-axis shows the RMS error, and we compare tributary delta with tree and our previous synopsis diffusion. So note that tributary delta is basically a combination of tree and synopsis diffusion. But what it shows is that the result that we get is not just the best of those two techniques, but it's actually better than the best. And it shows the effectiveness of this type of hybrid topology. So concurrent to my work, there are 2 other works that uses multipath for aggregation. And one was from Stanford by Bawa et al. And other one was from Boston University by Considine et al. And the way my work is different from theirs is that we provided the formal framework. We tried to formalize the whole general class of algorithms so that you can prove correctness, you can analyze the errors, and so on. And we also looked at more systems aspects like the implicit acknowledgement or adapting the topology and so on. And the work on and our idea of using synopsis is very similar to the work used in traditional data streams. And in traditional data streams used by the database community, there they assume that the model is centralized, and they only consider order insensitiveness. There has been extension where the model is considered to be either distributed or duplicate insensitive. Our order and duplicate insensitive synopsis is more challenging than those because we need it to be both distributed and duplicate insensitive. And we have showed that this can be possible, and we also provided the general framework for that. Whereas those work, they basically solved one particular problem, and they gave an algorithm for that. That's it. Okay. So in summary, for data collection, I have shown synopsis diffusion, adaptive rings, tributaries, and deltas. And all those give us more than 2 times more reliable aggregation. And it doesn't require any additional resources. So any question on this part? So now I will come to the second part. This will be very small. This will be very short. So as I mentioned before that for end-to-end robustness, we need to make both those components robust. So I have talked about the robust collection part. Now I'll talk about robust storage part. So in a sensing system, like in the ocean monitor, the data collected from the sensors on the coast, they are stored on the machines on the internet. So now if a machine fails, or if it is not reachable because of network failures, then the system becomes unavailable. And our goal is to improve the availability of the whole service because of that type of failures. And the traditional techniques of, so at a high level, this system is like a distributed read-write database. And the traditional technique of making them robust is to use replication and some quorum systems. Okay. So initially, we used this type of techniques in IrisNet, and the experience was not that good as we expected. For example, we found that those techniques are not very effective in wide area system. And even after we replicated the data 7 times, 1 out of 100 requests failed. Okay. And to see what's going on, I started 3 very large distributed systems. I collected like more than a year long failure traces and tried to see what's going on there. And I identified the reason, and it was the large near simultaneous failure, which means that a large number of nodes fail within a very short time so that the system can't react with that. And this might happen because of like worms or DOS attacks or this type of failures. Okay? And the way they can affect a traditional replication and quorum system is the following. Suppose we have replicated the data in 7 machines, and we are using, say, majority quorum system, which is a standard quorum system where you basically need at least half the machine to access that data. So the sensor writes to 4 of the replicas, and the user reads from 4. Okay. So now, if there is a large failure, and if 4 of the replicas fail, none of them can actually access the data because they don't have 4 machines. And those techniques do not allow you to read and write only using 3 machines because they want to make sure that the user always gets latest data. If you don't have this constraint, you actually can't ensure that. Okay? So we have observed that in sensing application, we can actually relax this particular constraint. And we have found that many sensing applications can actually occasionally tolerate stale data. For example, in the ocean monitor system, scientists occasionally make snapshot queries like give me all the riptide events on West Coast. Okay? So now the sensors on the West Coast, they are actually not time synchronized. Some of them can be slow and some of them can be even partitioned from the network. And in that case, the data that the scientist is getting, some of the data is stale. So the snapshot that you are getting, it will be inconsistent. It will not be consistent. Some data is old, some data is fresh. And this is very common for any large scale systems. So the question is, how can we tolerate that? So the sensing applications can tolerate them by a number of ways. For example, they can look at the timestamp of the data. And if they know that the data is not changing very rapidly, then if they know that the data is like 10 minutes old, that's probably fine for them. So they can use these application level semantics to tolerate this type of staleness. Then the question is, how can we actually use this fact in our system design? So another researcher from this IrisNet project, he proposed a new type of quorum systems called signed quorum system. And the way it differs from the traditional quorum system is that in traditional quorum system, you don't have any inconsistency. And for achieving that strong consistency, you give up availability. But in this new quorum system, you allow a very small inconsistency. For example, one stale read in 1,000,000 times. But for that very small inconsistency, you can improve availability by an order of magnitude. Okay? So we use these signed quorum systems in IrisNet. And when he proposed this quorum system, it was in Port C, so it was very theoretical paper. So it was not studied under near simultaneous failures. So I studied under near simultaneous failures, and I have shown that signed quorum system is more effective than traditional quorum system for tolerating this type of failures. Okay. Okay, so IrisNet was the first implementation of this type of quorum system, and here is the availability that you get from one of the real systems. The x-axis shows the number of replicas, y-axis shows availability in terms of number of nines. And as you can see here, like if we use like 7 replicas, the gap is like 1 extra 9. Okay. So there are some other systems that use replication for tolerating correlated failures, like Total Recall or Glacier. And the way our work differs from them is that we consider read-write data, but they consider only read-only data. So read-write data is more challenging to consider in this space. Okay. So basically, for robust storage, my contribution was I showed that signed quorum system is a good fit for this particular application domain, and we have implemented that, and it shows that availability can be improved by an order of magnitude without any additional resources. Okay. So this is the contribution slide for end-to-end robustness. For data collection, I have shown like 2 times more reliable data collection without extra overhead. For storage, I have shown an order of magnitude more robustness without extra overhead. So now I will very briefly talk about my other research, and we can talk about them in details in one-to-one meeting or after the talk. Okay. So I have worked on distributed XML query processing in the IrisNet infrastructure. So in IrisNet, the data collected from the sensors are stored in a large XML database. And the way our XML database differs from other existing XML databases is that in the existing work, they consider a collection of XML documents. So suppose you have like 1,000 XML documents. And when you make a query, you need to explicitly tell which documents you want to consider. But in our work, we consider all the data in a single large XML document. So user actually doesn't know whether it's distributed or not. To him, we give a very good transparency. He knows that there is just a single document. And we basically distribute it transparently. And second, we support a standard query language on that distributed database, which was also novel to this work. Okay. I also worked on function caching in the context of IrisNet. So as I mentioned before, IrisNet is a shared infrastructure. So more than one application can run on it at the same time. So I have implemented a mechanism where different services running on the same time, they can share each other's resources, each other's computation. And it seems that this gives a lot of scalability for sensing devices. So I also worked on a model for programming a collection of sensors. So suppose you have a large collection of sensors. The question is how you actually program them. So the approach that we take was a standard database interface. So user can use standard database things like long-running queries or triggers or snapshot queries to define what he wants. But at the same time, it is extensible. For example, the oceanographers now can say that detect all the riptides near Australian coast. It's a functional type of statement, declarative statement. He doesn't need to know what sensors are there, how the data is distributed. He doesn't need to know about that. At the same time, it has a procedural component that basically defines what particular algorithm it should use. So it gives us, at the same time, it gives us a declarative interface which is simple enough to use, and an extensible procedural component which people can use to define the exact function. I think I'll skip that. Okay, so in future I would basically want to work more on heterogeneous sensors. So in IrisNet we have already considered sensors like motes and microphones. They are very different in nature. But there are lots of unresolved issues which we don't know the answer yet. Say for example, given a high-level task, we don't know how to automatically break it down so that some component will run on the internet-connected hosts and some part will run on the mote type of network. We don't know how to automatically break it down. The programming model that we proposed is actually suitable for the internet-connected part of the network. And I would like to work on a single programming model that will basically work for the different types of sensors. Okay. I would also like to work on actuation and mobility of the sensors. And it gives us a number of challenges. For example, when the nodes moves, how we can adapt the topology. But at the same time, it gives us a number of advantages. For example, we can now move the nodes for maximum coverage or for network repair. And all those things need some sort of distributed coordination problem. And finally, all those things have some sort of cost related with that, like sensing, actuation, mobility. And I would like to work on some richer interface so that user can specify how much cost he wants to spend for a certain task and how much precision he wants to expect from them. Okay. So, I mean, I believe that the sensor network research requires a broader focus. I mean, so far we have worked mostly on small sensors, wireless sensors. But I don't think that that's the only sensor that I should work on. I think in near future, the sensor network will be more heterogeneous. It will be larger scale, and the sensors will be shared. And this actually gives a lot of new challenges. For example, although you want heterogeneity, we somehow need to abstract that away from the user. So it's some sort of, there should be a layer that hides what sensor you are using. Okay. Then we need to make it scalable, robust, and plug and play. I just buy a sensor and put it in the network. It becomes part of the whole sensor network. And finally, it should be shared and it should be dynamically programmable by users. And my future research basically would be around those topics. Okay? And thank you. So any question? Yeah. So it's even true for tree, right?
No, because if you don't have the synchronization.
In the tree, they have the synchronization between parent and child.
But it's still people
No. It's actually the same.
not necessarily.
No, that's not necessarily true.
Yeah.
Just a tiny bit.
Yeah, right.
So
Yeah.
you create like a how does it
It doesn't work well.
It doesn't work well.
Yeah, so I mean, yeah, there are problems there, sure. But the thing is, whatever works for tree should work for this type of topology too. Layers means or rings. Okay, okay. Yeah, sure. It's also true for tree because in tree, you basically divide it by the height of the tree because the leaf nodes should first send, then their parent send, then their parent send. But in some sense, there's a dependency here, right? Because if you want to send exactly one message, right? So every node needs to send. The tree is doing aggregation. Yeah, it is doing aggregation. Any other question? Okay. Great.